So welcome back, everybody, and to this lecture on quantum computing. And we are going today to discuss first a review from last week with 1 qubit gates and 1 qubit Hamiltonian. So we are going to partly use slides and also the whiteboard from last week and link this much more with project number 1. And then we are going to have a small digression into entropies and how we can use these to classify entanglement. And this leads to what's called the von Neumann entropy, which is the quantum mechanical parallel to what's called the Shannon entropy, or what we normally call for the classical information entropy. So quantum mechanically, we have to change that equation a little bit. And this means that today, we're also going to review a little bit about the density matrices. The topic of density matrices and measurements becomes also relevant for project number 1, because when we simulate a quantum mechanical system now, we're actually going to make measurements on the system. And the second part is us moving into the qubit Hamiltonian, the simpler one. And that qubit Hamiltonian is something which we will also see how we can simulate. So these two Hamiltonians which we have chosen are nothing but 2 matrices or Hamiltonian matrices. One is a 2x2 matrix, it's a 1 qubit system. And the other one is a 4x4 matrix, which then represents a 2 qubit system. And we are going to look at some of the basic properties, which we will also see in the other projects and also in the other parts of project number 1. So what I'm going to do first now is actually go a little bit back to the whiteboard and repeat some of the things which we discussed last week in order to motivate both density matrices, measurements, why we insist on these properties and or quantities, and then to link this with what's called the von Neumann entropy as a way to discuss the degree of entanglement which is a system exhibits. Now, one thing which I wanted to anticipate as well is the fact that if we look at this system, this 2 qubit system, this is a system where we will see how we can actually entangle 2 specific states in order to produce an entangled state, which then can be used to actually construct gates, which then perform operations on, let's say, 2 qubits. So the simple Hamiltonian, which we have, this 2 qubit Hamiltonian, allows us to catch more than just one bird with one stone, because we are going to look at how we can use that one to discuss and motivate a little bit later how we construct the gates by entangling states. But this is something which will come a little bit later. So let's switch over to the whiteboard and remind ourselves of some of the basic things which we looked at last week. So this is a repetition from what we did. Now, the simple Hamiltonian which we have is a 2x2 matrix, and it represents a 1 qubit system. And we wrote a Hamiltonian last week. And this is the first one you really encounter in the project, in terms of one piece, which we call the unperturbed part, or the non-interacting piece. And then we had an H1 here. Now, this is meant to represent a system which you can think of a 2-level system. So this H0 here is then just given by a diagonal matrix. So we have an E1 and E2 here. And these E1 and E2 states are constructed so that they are eigenstates of the computational basis which we have. So when H0 now acts on the computational basis, so the basis we have chosen is a state 0, which then is going to be the eigenstate of this E1, has E1 as eigenstate, and the state 1, and we represent them in the standard representation, which we have been using throughout the semester here. So we have 1, 0 and 0, 1. Now, these states are eigenstates of this Hamiltonian with eigenvalues E1 and H0 acting on 1, which gives us E1 multiplied with the state 1. So we say that this H0 is an operator which has the computational basis as an eigenbasis. Then we have what we would call an interacting piece. And later you will see when we, in the second part of the semester, when we are going to discuss quantum sensing, we can actually replace this H1 or HI with a time-dependent interaction, which then could be thought of as a perturbation of the system, a time-dependent perturbation of the system. And what we did then was to rewrite a little bit the Hamiltonian. So we could actually show that we could rewrite this Hamiltonian last time. So this H0 is something which we could rewrite in terms of a E1 plus E2 divided by 2 multiplied with the identity matrix, a 2 by 2 identity matrix. So this matrix is just 1, 0, 0, 1. And then we have an additional term, which is given by E1 minus E2 here, divided by 2 times a Pauli Z matrix. And that Pauli Z matrix, just to remind you, is given by 1 and minus 1. Then the interacting Hamiltonian is something which we could rewrite in terms of some slight manipulations. So we could rewrite it like a V11 plus a V22 divided by 2 multiplied with this identity matrix plus a V11 minus a V12 here. So this should actually be a it's a V22 divided by 2 multiplied with a Pauli Z matrix. And then we had the non-diagonal part, which is something which we would rewrite in terms of a V of x times x, where this V of x was now the non-diagonal matrix element, V12 or V21. And x is just the Pauli X matrix, which is then given by 0, 1, 1, and 0. So in that way, we could actually rewrite the Hamiltonian. And if we now look at what we have to do then, is the following. We need to calculate specific quantities. So when we are going back to project 1 here, what we have is a Hamiltonian. When we diagonalize this Hamiltonian, we diagonalize what we're going to have then is a eigenstate phi. This could be the lowest one. We are going to have 2 eigenstates. We will have an alpha. We can call this a psi 1. This is an alpha times 0 plus beta times 1. And then we could have a second state, which would then be given by a constant gamma plus a new constant delta. And these are complex constants. So we have a 2 by 2 matrix. We obviously get 2 eigenvectors, and they are linear combinations of the eigenbases which we have chosen. So if we look at the Hamiltonian which we have, if we go back to these expressions here, you see that we can actually rewrite this Hamiltonian in terms of a term, which we simply label as this. So this is what we actually need to calculate now when we are going to calculate the expectation values. So we could take any of these states, phi of I, with x, sorry, not x, but the identity matrix. So these are the quantities which we are going to need to evaluate times phi of I. There's going to be a plus a constant d and phi of I, and then we have x, phi of I, and we are going to have an additional constant e, which now contains this Pauli Z matrix. So in principle, our Hamiltonian now contains these different parts. So this is one of these two states, phi1 or phi2. So when we now are calculating, so when we look at this Hamiltonian here, so what we need then is, so I forgot to put the expectation sign here. So this is an expectation value of the Hamiltonian. So when we have this state, then we can actually go back and calculate the energy, but normally that is a waste of time because when we diagonalize, we get the eigenstates and the eigenvalues. But when we are going to make a measurement, we need actually to do something like this. So the whole thing then is that these states, phi of I, they are going to be given by some initial state of the system. So let's call the initial state for some phi. This is the way we initialize the system. And now I'm not going to put a subscript 1 or 2. And when we now act on the system, what we are going to get is a new state. So when I act on it, this will give us a state phi prime times some constants times some eigenvalue. Now, in general, the way we are going to perform these operations is to initialize our state. So the typical initial state could then be a state 0, just to give you an example. And we will act on this with different gates. So we are going to set up, as we discussed last time, a set of unitary transformations. And these unitary transformations will then, at the end, lead to a final state on which we are going to perform the measurements. So if we now look at one possible way is to take this initial state, 0, and then prepare it through specific rotations and rewrite this one in terms of a state on the block sphere. So this one is now, if we now look at a 1-qubit system, then what we have, we can define a general state, on the block sphere. So let me just write this down properly here. As, and then we will just write this state as a cosine of theta half acting on the state 0. So this would just be an arbitrary state on the block sphere. And this is multiplied with the sine of theta half multiplied with 1 here. Now, what we defined last week was different rotations. So we could then define something which we called a rotation. One way to achieve this is to perform specific physical operations. And these were rotations around the x-axis, rotations around the y-axis, and rotations around the z-axis. So what we had then was a rotation along the x-axis, which we could then define as an e to the I of theta times sigma x divided by 2 here, which then is given by a cosine of theta half multiplied with the identity matrix, and this is a 2 by 2 identity matrix, minus I times sine of theta half multiplied with the Pauli X matrix, which is also a 2 by 2 matrix. So this is one rotation. We have a similar one for Y. which then simply becomes cosine of theta half multiplied with the identity matrix minus I times, and this is given by a sine of theta half multiplied with the Pauli Y matrix. And then we have a similar one for the Pauli X matrix, a Pauli C matrix. So what we could do now is to think of the initial state. So the initial state could now be modified, is modified to become a general state, modified to, so we get this phi, and we could think of this as a general state with an Rx times an Ry, an angle theta. We have an Rx, an angle phi, multiplied with the original state. So that means that the state which we have is going to be a state which depends on the angle theta and phi here. So this is a general initial state, which we can initialize the system in this specific way. We assume now that we know that the state is in the lowest state. So if you're thinking of a system which now has just two qubit states, 0 and 1, then we initialize our system to be here. And by performing these operations, we're actually getting a new state. So these are essentially rotations of the system. And the way we would indicate this graphically is in terms of a circuit. Graphically, what we would have then would be, and this goes from the right to from the left to the right. So we have the initial state. We have a rotation around the x-axis. So this is Rx. And then we have a new rotation around the y-axis. And this gives us a state phi. Now, what we want afterwards is actually to calculate these specific expectation values with these states. So if you now look at this Hamiltonian which we had, and this state, which we now have prepared for specific operations, then what we would get now is an expectation value of the Hamiltonian with respect to this state here. So we don't know these angles. So the recipe which we are going to develop with something which is called the variational quantum eigensolver is to introduce an optimization scheme where we minimize the energy with respect to the angles theta and phi, which we don't know. So this is where the optimization part comes in. So this algorithm, which we will discuss in more detail next week, is an algorithm where we now will prepare the system in a specific state. We perform rotations, and the optimization part is then performed on a classical computer, but the measurement is performed on a quantum mechanical computer or quantum computer. So let me see now, there's a question online here. So it's pretty common to actually start with a state 0, because you could think of you being able to prepare the system in its ground state. So this state 0 doesn't need to be a single particle state, but it could represent a complicated many particle state. So there is a question in the chat here. Sorry, you mean that we start always from 0 to construct our initial state through rotations? Yeah, it's pretty common to do that, because you often know that if you cool the system down at a specific temperature, at a very low temperature, then you may expect the system to be in its ground state. So we know the initial state of the system. And then we prepare it so that we reach a specific arbitrary state, which is now given by these parameters. So what we are going to deal with next week is the calculation of, so the expectation value of the energy is now going to be a quantity which will depend on these angles, theta and phi, for the 1 qubit case. And this is going to be given by phi of theta, phi here, of h, and then phi of theta of phi. And the optimization part, which is done on a classical computer, so this is classical calculation. This part means that we need to evaluate this energy as a function of the angle theta. We want that one to be 0, the gradient of that one. And we need the gradient with respect to the other angle, phi, and we want that one to be 0. So the typical way we solve the classical problem is by some gradient descent method, which is the classical optimization scheme. This is something we will come back to next week. So this is the first part. So we will put a 1 here, and then we have a part 2 here, which is then the evaluation on a quantum computer of the expectation value of phi of h on a quantum computer. So that means that what we need to evaluate now on a quantum computer is phi of 1 of phi, and we need to evaluate for this specific Hamiltonian the expectation value of z of phi and phi of x. So we need these 3 expectation values, and the typical way you would do this on a quantum computer is actually to repeat these experiments many, many times. So you would perform these measurements a given number of times, and then you would take the average of all the measurements which you make. So the way you would also implement this on a real quantum computer is that you rerun this again and again. So you would typically run, let's say, 1,000 experiments, and then calculate these different expectation values. Now, these steps 1 and 2, they make up what is called the variational quantum eigensolver. And that is the most used algorithm for studying quantum mechanical problems on a quantum computer. So 1 plus 2 here make up, and this is what we will discuss in more detail next week, make up the variational V for variational, Q for quantum, and E for eigensolver. Solver algorithm. Now, historically, the algorithm which was introduced first to find the eigenvalues of a specific quantum mechanical system is something which was called the quantum phase estimation algorithm. And that was based on us introducing quantum Fourier transforms. Now, this algorithm requires a long chain of operations which become less feasible in the era which we are in now, which is normally called the noisy quantum computing era, because many of the states which we are going to simulate, they don't have long enough lifetimes to be able to perform a long chain of simulations. So this is the standard algorithm which is being used in order to solve quantum mechanical problems on quantum computers. So the next week, we are going to look into more details on how we actually set it up. And we're going to give a reminder of the optimization part, which is essentially a gradient descent method. But before we do that, I wanted to go back a little bit to these expectation values and the measurements which we're going to make. So the kind of measurements we want to make are measurements which are done in a computational basis. So the ideal for a measurement is to make the measurement measurement in the computational basis. So this is the basis we have chosen, and which reflects the physical states of the system, which we have chosen to use as the computational basis itself. And in our case, we know that if I take the identity matrix and act on that with this state, this is just equal to that state. If I act with it on the second qubit state, this gives us the second qubit state. So these states are eigenstates of the identity matrix. We know also that if I act on this with the Pauli Z matrix, this gives me simply the Pauli Z matrix. And similarly, if I act with this on the state 1, I get back the state 1, but I have a minus sign. So this is just an eigenstate with an eigenvalue equal to -1. So when we're making the measurements, we would like to transform these different matrices, like the Pauli X matrix, into a Pauli Z matrix. Now, if I do this, I get state 1. So you see now immediately that the Pauli X matrix is not the basis which we have chosen is not an eigenbasis of the Pauli X matrix. And if I act on this one, then we normally call this for a spin flip operation. So that means that when we now look at the states, we would like to make a transformation of this Pauli X matrix to a Pauli Z matrix. And this is something which can be done by using the so-called Hadamard matrix. So let me just show you that. So if I look at the Hadamard matrix, this is another 2x2 gate. You can increase this to more than just 1 qubit. So this matrix is just given by h, 1 divided by square root of 2 here, of 1, 1, 1, and -1. And this is a matrix which then entangles a specific system. So we know that if I act on this with this Hadamard matrix on the state 0, I get 1 over square root of 2 of 0, and then I get +1 here. So I have created a linear superposition. If I act on this state 1, then I get 1 over square root of 2 of 0 -1 here. So I create a superposition. Now, this Hadamard matrix represents actually specific physical processes. It's something which we can think of. If we now look a little bit closer, we can see that this Hadamard matrix can actually be rewritten as two famous matrices. So it can be rewritten as a Pauli X matrix plus a Pauli Z matrix. And it's pretty easy to see that because this one here is nothing but 1 over square root of 2. And then I have 1 -1, 0, 0, plus 0, 1, 1, 0. And this is a C matrix, and this is a Pauli X matrix. Now, it has some important properties. The matrix, if I take the operation here, then we see that this is a unitary matrix. So it obeys the properties which we want to have. 1. And the inverse of the matrix is just equal to the matrix itself. Now, there's a very nice property here, is that we can actually rewrite. So think of these gates now as physical operations which we are doing on the system. And as we discussed last week, like this Pauli X and the Pauli Y and the Pauli Z rotations which we're making, they can actually represent specific physical processes acting on the system. Like last week, we looked at this Larmor precession, which then could be represented by a Pauli C matrix. So the nice property which we have is that this Pauli X matrix can be written out as a Hadamard matrix times a Pauli C times a Hadamard matrix. So what we are doing now is that we are preparing for making a measurement. Now, if I make a measurement of my system in this state phi, which we have here, but then I'm making a measurement where I write it out like this, with just the X matrix, then since this state here is a linear combination of a qubit 0 and a qubit 1, when I then calculate this expectation value, these states which are making up the state phi are not eigenstates of the Pauli X matrix. So what I'm going to do now is to make a transformation of this one so that it can be rewritten in terms of a Pauli C matrix times some transformed state. So let's look at how we do that. So it's easy to see this because if I look at this quantity, no, not that one. I actually rewrote it in the wrong way. It was not like this I wanted it. It's actually the Pauli C matrix can actually be written as a transformation with the Hadamard transformations times the Pauli X times the Hadamard matrix. And you can see this now by simply writing out, because this would be the same as X plus Z multiplied with X multiplied with 1 over square root of 2 here of X plus Z. And this is simply equal to the half. And then I have a Pauli X squared times X plus a Pauli X squared times Z. These are matrices, so I have to take care of the order of the multiplications now, plus a Pauli Z times X times a Pauli Z. Now, we know that these matrices, when they are squared, they're equal to themselves. So this is equal to 1. And that means this is also equal to 1. And what we have then is that this operation which we have here, this is actually the same as minus X. You can actually show that. And that means that when I collect everything, I'm going to have a minus X here, which cancels this one. I get 1 times C plus 1 times Z plus 2 divided by a half. So this is simply equal to the Pauli C matrix. So how can I then do the measurement of this specific state which we have, phi, with the Pauli X matrix and phi? Now what I can do then is to think of this, and now I'm just multiplying. So what this means, due to the Hermitian properties of the matrices, I can actually rewrite this as a Pauli, as H times Z, which is equal to X here. Because you have these properties of the matrices. So using these properties, if I multiply now with the Hermitian conjugate and H here, and since this is a real matrix, the matrix is real, so that means that when I take the Hermitian conjugate, it's the same as H. And you see that from the properties which you have here. So it means that H Hermitian conjugate is the same to H. So when I multiply with H here and H here, then I get 1 and 1, and that gives me simply X. So that means that I can rewrite this one in terms of phi, and then I have H times Z times H times phi. Now, the way I can look at this now is as a transformed state of H of Z multiplied with H of phi. And we can call this for state phi of Z of phi. But where the state phi prime is still a linear combination of qubit 0 and qubit 1. So that means the following. When I'm now setting up a circuit for making the measurement, so our circuit then for the measurements, so we are going to calculate, for instance, the phi of z of phi. This is one expectation value. So we would simply write this as a state 0. We perform a rotation, Rx. We perform a new rotation on Ry here. We then apply the Pauli C matrix here. And this is where we are going to make the final measurement. So this is one transformation which we are now going to make of this state phi here. Sorry, state 0. Okay. So this is my transformed state. So I get my new state phi here. And then I plug in the Z matrix. And then at the final point here, I can now make a measurement, which I indicate like this. So the measurement I'm making is actually of this specific quantity here. Now, if I now look at my next state, this zero state with the Pauli X matrix, I perform a transformation here. I perform a new transformation. And then I'm going now to perform a Hadamard transformation. I have a Pauli Z here. And then I have a new Hadamard transformation here. So that's the way I'm going to set up this operation here in order to calculate this quantity, which is H times Z of H times phi. So the state itself, if you look at the change of the state, so the state, so I'm just going to bring this back here. The state itself is going to change as state changes as, so we have a 0, and this is going to change to this by this Rx, and then I get an Ry, and this is my new state, and this is when I'm going to calculate the expectation value of this quantity. And then for the next one, what I need to think of is the change of Ry, and then I perform a Hadamard transformation, and this gives me a new state, which I'm just going to call phi prime. And then with that specific state, so here we can then calculate phi of Z of phi, and here we can calculate phi prime of Z of phi prime. So this is a quantity. So next week, when we are going to discuss the VQE in more detail, we are now going to use these transformed state in the evaluation of these specific expectation values. So when you run the experiments, this quantity here needs now an Rx gate, an Ry gate, and a Hadamard gate. Here, for this specific measurement, I need an Rx and an Ry gate. So this is how you would set it up experimentally. And experimentally then, you would rerun this again and again, and then simply accumulate the number of times a specific event was seen and divide by the total number of events you have. Okay, this was a slightly long repetition of what we did last week, but we need this element in order to prepare for what is coming next week. Yeah.
So we started with the state that is
zero. Yeah.
Then the transformation and Rx and Ry are just rotation.
Yes.
And it's just to express a general state.
Yes.
And then when we go and measure,
yes,
we will end up in one of the two classical states, right?
Exactly.
But before we measure, you want to put it in the correct base.
Exactly.
Correct? And that's why we do this.
Yes, exactly. Because when you make the measurement at the end, you have to make a measurement in a specific basis. And in our specific case, we have chosen a basis. This is just due to the way we have chosen the basis. So we have chosen a basis which is given by this qubit 0 and 1. And these are eigenstates of the Pauli Z matrix or the identity matrix. So the whole thing now, when we have rewritten Hamiltonian in terms of Pauli X, Y, and Z matrices, so what we did, if we just go back a little bit, is to take this original Hamiltonian, which we put up here, this one, and we rewrote that one, this term here, plus that one. We just rewrote that one in terms of an identity matrix, a Pauli X, and a Pauli Z matrix. Because the whole thing is that these matrices represent actually physical processes which you can implement on the system. So the whole way of thinking is that you, instead of solving a differential equation, you're actually thinking of solving a problem where you manipulate with an experimental equipment specific physical states. So it's a totally different way of thinking of solving a physics problem. And then since you have chosen a basis, which then often is given to you by physical states of the system, then you're manipulating these physical states. So when you're developing a quantum computing platform, you need to have platforms where these energies are well defined and that the states which you are dealing with can have a specific lifetime and that you can manipulate these states with the experimental equipment, which could be a magnetic field, where the frequencies actually match the energies of the system. And this is a delicate experimental part, which we in a way drop here because we just take that for granted that this can be done. But this is a huge quest experimentally to find platforms where you can perform calculations like this. So it's a totally different way of rewriting a problem compared to what we are familiar with. Okay, so I wanted just to go quickly back before we take a small break. And I'm going to go back to the slides here. And in the notes this week, you will see that there is a reminder from last week about the density matrix and traces. So I just wanted quickly to remind you about these quantities because after the break, we are going to look at one way by which we can extract information about entanglement in a physical system. So we defined a given operator using the spectral decomposition. We could define that in terms of the eigenvalues and the eigenbasis, which is assumed to be an orthogonal eigenbasis. And an operator, which is a function of this operator A, can also be written out like this. And the trace of a product of matrices is cyclic, which means that this equation here has to be obeyed. And we also have that the trace of these operators, or the trace of this specific quantity which we have here, is now given by the expectation value of the operator itself. Now, the density matrix is now simply defined as the spectral decomposition where we have the probabilities. So these probabilities then represents the overlaps of being in a specific state. So if you go back to this one qubit case, which we have right now, so let me quickly remind you of that. So before we take a break here. So if we now look at this one qubit state, so let's just go back here. And we have defined the state phi, which is a linear combination of alpha multiplied with qubit 0 and beta multiplied with qubit 1. Then the density matrix for this specific state phi here is now simply given by the probability of being in a specific state. So in our case, we actually have only two states here. And this is now given, so this specific state here, if we just write it out, is this density matrix is defined in terms of these two quantities. And you will see then that this becomes equal to alpha squared plus, and this is multiply with 0 and 0 plus, and then we have alpha times beta of 0 with 1 plus alpha times beta of 1 with 0 plus beta squared of 1, 1, which is then equal to this matrix with alpha squared. And then I have alpha times beta, and then alpha and beta squared. And if I take the trace of this quantity, rho of 5, this is equal to alpha squared plus beta squared, and that is equal to 1. And what we have here, these coefficients, which you see here, these ones, this represents the probability of being in 0, and that represents the probability of being in 1. So when we then write the density matrix in this compact form in terms of the probability, that means that these different coefficients, they represent the probability of being in one of these specific states. And we can see that immediately when we take the trace here. So let's just go back to the whiteboard, no, to the slides, to the Jupyter notebook. And the quantity which we have here is actually given, so the density matrix can actually be written out in terms of these probabilities. And these are the eigenvalues of the density linked with one of these orthonormal basis states. And the quantity can then be transformed, these states can be transformed by unitary transformation. And these are the gates which we are applying on the system. And these unitary transformations have obviously to obey the requirements of unitary transformations. And we can actually rewrite it like this in terms of unitary transformations. And we know that with a unitary transformation, it's actually easy to see that the trace of the transformed density matrix also has to be equal to 1 because the trace is cyclic. So what we're going to do after the break is actually to revisit the way we do measurements, and we are going to look back again at these Bell states. And when we've done that, we are going to look at the definition of entropy and how we can use that as a measure of entanglement and see what it actually means when we look at a specific Hamiltonian system. So welcome back. The topic now is to first remind ourselves a little bit about the entangled states. And then we are going to look at a measure, and actually there are more measures for entanglement, but the entropy of the system is something which has been widely used. Now, this entropy is something you will encounter if you want to study these ways of, let's say, measuring entanglement. It's something you will encounter in many different disguises. So the measure which we are going to give, the von Neumann entropy, is just one of the ways of extracting information about an entangled state. Now, I'm going to use the Jupyter notebook a little bit now, also because we are going to look at the two-qubit Hamiltonian, and we're going to look at that one and try to understand how we can actually create an entanglement in a two-qubit system. So some of the states which we encountered last week and the week before were these Bell states. And in this case, what we did was to construct a computational basis. We're using two qubits. And we have the qubit 0 and qubit 1 for system A and system B. And we could think of these as two isolated systems or two distinguishable systems. And we can then create through a tensor product, a state which is, we label as 0, 0, 0, 1, 1, 0, and 1, 1. So this is now a computational basis. So when we come back to that, the two-qubit Hamiltonian, which we are going to introduce just in some few moments, then that two-qubit Hamiltonian will have parts of the Hamiltonian, which we are going to call the non-interacting part, or this H0 part, which we introduced in connection with a one-qubit case. And that part will have this computational basis as an eigenbasis. And then we are going to add a perturbation to that afterwards. Now, the Bell states, which we discussed in the beginning of the semester, I think it was even the second and the third week, we have 4 different states, and we had one exercise where we could show that these are, again, orthogonal and define an orthogonal basis. So we have the 5+, and we're just going to look at the first one. But then we have 3 more. And these are states which cannot be written out as product states. And we have called these entangled because we know exactly the system here, the 2-qubit system, but when we make measurements on them, it's only in few exceptions where we can actually say something when we measure one of the qubits, what is the state of the other qubit. So these are the states, and I'm just going to go down. So when we make a measurement, since we now have a 2-qubit system, and the reason why I bring this up is that when we make a measurement, you have 2 now independent systems. And we are going to make a measurement on one of these systems. And hopefully then we can say something about the other system. So when we now measure one of the qubits, that one of the things we can see for this specific case is that automatically determines the state of the second qubit. So when we now make a measurement, we need to remind ourselves about these projection operators. So if we make a measurement on the state in system A with the qubit 0 and qubit 1, we have to define projection operators. So in that specific case, what we end up with is now constructing a one operator which projects down qubit 0 in state A and taking the tensor product with the qubit B or system B, but nothing happens on system B. So this projection operator, which now acts on qubit 0 in system A, can then be written out in terms of the matrix you see here. Similarly, we can now define the projection on the, so this should be actually for the one state, for the qubit 1 state in system A, in terms of the outer product of the qubit 1 in system A, and then tensor product with the identity matrix for system B, because nothing happens in system B. And when nothing happens, we just rewrite that in terms of the identity matrix. And that gives us this specific matrix. So when we then make a measurement, this is actually what we end up doing. So when we, next week, are going to look at the way we are going to set up measurements in order to find the expectation values of the Hamiltonian, this is exactly one of the recipes which we will follow. So in this particular case now, we have a system which is given in an entangled state, pi plus. So our final system, so if you think back of what we discussed before the break, when we prepared an arbitrary state for the variational quantum eigensolver, you could think of your quantum eigensolver with these rotations having resulted in a state phi plus. And now we want to make a measurement. So making a measurement means us making a projection. So just keep this in mind till next week, when we are going to look at the explicit implementation of the variational quantum eigensolver. So the only thing we have done till now is simply to prepare the system for what is going to come. So when I make a measurement on qubit 0 in system A, this is now done by this specific matrix. So keep in mind now, this measures a qubit in system A. And I'm projecting out qubit 0. So that gives me a factor of a half when I do that. And similarly, if I take the other one, it shouldn't come as a surprise. It means that I get a factor of a half. So after measurement, my state is now given by this normalization constant times the qubit 0 here. So this is now the final state where we now have performed a measurement of qubit 0 in system A, multiplied with the identity matrix for system B, and multiplied with the original state. So what, after measurement, I end up with the state 0, 0. So I make a measurement on 0, and that tells me that the other qubit has to be in state 0. If I do this on the other state, I make a measurement of qubit 1, and that simply projects out the 1, 1 state. This is my final qubit system of system A and system B. So these slides which you see here, or this information which you have here, is something which we are going to reuse next week when we are going to look at measurements of a specific state which we produce in the variational quantum eigensolver state. Now, if you now look at the entanglement, then if we take the states, I'm just going to scroll down a little bit because I wanted to discuss a little bit about ways of extracting information about entanglement in a specific physical system. So the standard entropy, if you now go back, and I don't know if you've taken a course in statistical physics or if you've taken a course in information theory, what we are interested in is a measure of a state and its likelihood. So we are looking after a way by which we can represent easily the likelihood of being in a specific system or in a specific state. So let me now switch over to the whiteboard and do some of the derivations on the whiteboard. So if you think of this quantity, which we call the entropy, and now we are going to limit ourselves to the classical information entropy. So what we want to have is a measure of likelihood. So you can choose how you want to give that information. And the simplest way to gain some kind of intuition about it is to look at a very simple case. So we can look at a binary system. And for a binary system, what I could do now is simply to say, if the outcome is true, I give it a probability of P. And if it's false, I give it a probability of 1 minus P. And since these are probabilities, it means that P must take the value between 0 and 1. Okay? So suppose now that I say now that P is equal to 1. So that means that we are in the state true, because then false is equal to 0. So we know exactly the state of the system. Okay? And now we would like to have a measure of this kind of exact knowledge. And you can cook up many functions, but one function which we could think of is to define a function which we simply call S, the entropy, where we could now try log 2 of P, just to give you an example. And now you see that if I put in P equal to 1, then S is equal to 0. So we could say that when the entropy is 0, we have an exact knowledge about the system. So it's just us finding a mathematical way by which we can encode the information. And then from a specific number, we can say, hey, if the entropy is equal to 0, then we know exactly in which state we are, period. However, if you look at that function, there are some requirements we would like to have. So some minimal requirements. And one of the requirements we often add to it is that it's additive. There's a reason for that. If you now think of you having independent and identically distributed events, and if you have two stochastic events, x1 and x2, then that would be given by a p1 of x1 times a p2 of x2. So having independent and identically distributed, so I'm going to have this as an uppercase P, and these are going to go P of x1 because they are identically distributed. So you could think of a stochastic event 1 and a stochastic event 2, which follows a Gaussian distribution. So they have the same form of the probability distribution. Now, if we then choose this minus s equal to minus log 2, I mean, it doesn't matter whether it says log 10 or the natural logarithm, because that just gives you a scaling parameter. So it doesn't matter whether we have log 2. You will find for this binary system, having log 2 is convenient because log 2 of 2 is 1, right? So else it just gives you a scaling parameter. Now this would then be, and this is this probability x1, x2, this would simply now be additive because I would have log 2 of p of x1 minus log 2 of p of x2. Sorry, p of x2 here, like that. So this is additive. We often want it to be a continuous function, especially if we have a continuous distribution. We normally want it to be non-negative, this measure. Probabilities are non-negative, so we want to have it non-negative. And we may also add more properties to this kind of quantity. And we could assume that it is a function which now is going to give us a result which is continuously increasing. So if we now look at this s, which is given by minus log 2 of p, if I make a plot now, I see that if I make a plot in terms of p, which goes from 0 to 1, and we put 0 here of s, we see that this function is 0 here when it's 1, but then it keeps increasing. So it's a continuous function. It's a function which is going to be additive, but it's a function which keeps increasing. So we don't know what happens if we now look at p equal to 0, you see now that this corresponds to us having false, because that is equal to 1 then. Because false has the probability of 1 minus p, which is equal to 1. Okay? So when I put p, if you look at my drawing here, if I put p equal to 0, I now also have another case where I know exactly in which state the system is. So this function which I decided upon, log 2 of p, doesn't now reflect the other case, which is uniquely defined, which is the false case. So what we could try now is another function. And this is the function which actually people end up with. So we could now try s, which is minus p of log 2 of p. In general, what we would have is now a probability s of x, where this now runs over all the x in the domain of possible events. So you could now think of having this x here to be given by some stochastic events, x0, x1, up to xn minus 1. So you make a set of measurements, and these are your stochastic. So x's are stochastic variables. And the way you would now define this is in terms of the probability for that specific domain. So you could think of this being a binomial probability. It could be a uniform probability, whatever. So we don't specify the probability of little x. And then we multiply that with log 2 of p. And the capital X here, the uppercase letter X, represents now all the possible stochastic variables which we can have. In this case, they are discrete, but there's nothing which hinders us having continuous events, okay? So this is just a set of stochastic variables which we have chosen. And this is now given by, so this expression here, if we now go back to the binary example, I have two possibilities. I have my true and my false. So that means that my S is now given by minus P. This is my true case of P minus 1 minus P. And P is a variable which now runs from 0 to 1. And then log 2 of 1 minus P. Okay? Now what I see now, if I make a plot here, is the following. So when P is equal to 0, then S is equal to 0. Because what I have is that lim of x goes to 0 of x log 2 of x is equal to 0. Then if I choose P equal to 1, so this is my false case, which is 1 minus P, uniquely defined. We know it's false, okay? And then if I take P equal 1, then I also see that S equals 0. So that is my true case. If P is equal to 0.5, and I plug in the values, then I find that S is minus log 2 of 1 over 2, which is the same as log 2, base 2, which is equal to 1. So if I make a plot now of my entropy from 0 as a function of P from 0 to 1, then I have 1 here, and this is a 0.5. I have a maximum here, and it goes like this. So these 2 points, this is true. Only one state, unique. This is uniquely defined. This case here is false, and that's uniquely defined. There's only one possibility. So at the endpoints, it means that we know exactly in which state the system is. That sound reasonable? So we're just looking after a measure. And now you see that the maximum value is when we don't know anything about the system. Because P equal 5.5 is the same as us tossing a coin. So you don't know whether it's true or false. And the probability is just 50-50. So that means that the top value is the less likely case which you have. So this is just less likely. So what we have is a function which is continuous, which is non-negative, which has a maximum value when the likelihood is of a specific event is just unknown. Or rather, the system, you don't know in which state the system is in. So if you understand this case, this is something which is easy to extend to more than just true and false. You can have a multi-class set of outcomes. But the basic message is what you see here. You want to have a measure of what is the most likely situation, and then you put entropy to 0. And in our case, it captures both false and true. And then you want to have a measure for the less likely or the more unlikely events. And then you just have an entropy which increases. So you cannot tell whether the system is true or false. Does that sound, it sounds logical, right? Now, the problem now is that you cannot use this quantum mechanically. And the reason why you cannot use it quantum mechanically is simply because in a classical system, we can define precisely a given state. Quantum mechanically, a given state is a linear combination of a computational basis. So that means that if we want to do quantum mechanics, we need to modify this equation here. So just to repeat, classically, we have just one case, P false or true in this simple case. And that means that we can nail down exactly where we are. However, quantum mechanically, the state which we are looking at is going to be a linear combination of a given computational basis which we have chosen. So that leads to the quantum mechanical equivalent, which is called the von Neumann entropy. And the von Neumann entropy is defined as follows. So just to remind you, so we have the density matrix. And the density matrix for the system A is given by a specific state now. So it contains these probabilities of us being in this system A. And this the psi j's, these are orthogonal and normalized basis states. So this is an ONB. And these PJs, they simply represent the likelihoods for being in a specific system. So the von Neumann entropy is defined as the trace of this quantity here. So it's a minus and a log 2. You don't need to have log 2. You can just take log 10. Again, this is just a scaling constant. And you see that immediately from this binary system, instead of log 2, you could take log 10. You would just get a different maximum value. So with log 2 here, you simply have 1. If you take log 10 basis, you would have 0.69 as the maximum value. So that's just a scaling constant. And this is the way you define that specific quantity. So how do we get that quantity? And I'm going back to the Jupyter notebook, because I also want to dive into the example, which is going to come pretty soon now. Nope, I just picked the wrong one here. So let's go back to the Jupyter notebook. And what you will find then, when you look at the von Neumann entropy, this is the way we would define it. So we have the density matrix of a specific system. Now, the density matrix, as I said, is defined like this. And this is back to what we had before the break. It's a semi-definite matrix. And the reason why we look at this now is that, as we also mentioned before the break, I can perform. So the density matrix is a matrix which has non-diagonal elements. However, I can find a unitype transformation which diagonalizes my density matrix. So when I do that, I have an orthogonal basis and I have a diagonal matrix. okay? So that means that along here, what I have are actually the eigenvalues, and these eigenvalues are the probabilities. In our case, these are just the coefficients of an expansion. So if you now look at this object, which we have, this is the density matrix log2 rho A. I can now perform a unitary transformation of this object. So I multiply with U from the left and the right. So this is what you have here and here. Then I just insert the identity matrix, which is the same as U Hermitian conjugate times U. And then I can redefine the first quantity as this quantity, the diagonal one. So there is a magic unitary transformation which diagonalizes it. Unfortunately, for more than a 2x2 matrix, there is no such magic one. But then what you have is U times this quantity, and the unitary transformation of this quantity is just log D of A, because that's also a diagonal matrix. Now, what we know then is that this transformation here is now given by the diagonals times log 2 of D of A. Now, this quantity, again, is nothing but log of the diagonal elements. And you can show that easily. So that means that if I take the trace here of this quantity here, that's the same as the trace of the diagonal elements times the log 2 of the diagonal elements. And that is, since now this is the probability, then I know that the trace of this quantity is nothing but a probability times the log 2 of the probability. And this is equal to the classical expression. So probability times log of the probability. And that is a measure of likelihood or unlikelihood. So it is 0 when we know in which state we are, and it's non-zero when we don't know the state. So this is the equivalent of the classical one, but now using a standard quantum mechanical description, which means that our entropy can then be rewritten in terms of the density matrix. So this is the link between the classical and the quantum mechanical entropy. Now, what we are going to do now is to go back to the 2-qubit Hamiltonian in project 1. And I wanted to finish the lecture today by discussing this system. And just keep in mind that we will continue next week with discussions of that specific system. So we are going to use now a system of 2 qubits, which we call system A and system B. So it could be our system now prepared in 2 different subsystems. It could be you having trapped an electron in system A, which is then far away from an electron in system B. And they can be thought of as almost independent of each other. And then we repeat this exercise, which we did with the Bell states. And what we can do then is now simply to set up the computational basis. And what I'm going to do now is simply to assume that this computational basis is an eigenbasis of H0, which is one part of the Hamiltonian. So it will only contain my Hamiltonian, then is going to be like this. So the basis, which I call H, or the 0, 0, 1, 1, etc., is an eigenbasis of only one part of the Hamiltonian. And then I'm simply going to add a Hamiltonian or an interaction piece here. And also I'm going to put in some non-diagonal elements. So that means that my interaction here is going to be given in terms of a Pauli X cross, tensor product with Pauli X, plus a Pauli C cross product with a Pauli C. And this is going to represent these additional elements. So my Hamiltonian will have a part H0, to which this computational basis I've chosen is an eigenbasis. So this is exactly the same thing we did for the 1 qubit case. We had a Hamiltonian part, which is H0, which had 0 and 1 as eigenstates. And now we do the same thing here. because at the end, when we are going to make measurements, we want to make measurements in that computational basis. And we are going to make a measurement on, let's say, qubit 1 or qubit 2, no, qubit in A or qubit in B. Does that sound okay? So this is just a rewrite of the Hamiltonian. And then what I'm going to do now is to diagonalize this problem. And I can now calculate the density matrix of, let's say, the ground state. So this is a 4x4 Hamiltonian. So I will have 4 eigenvalues. And what I could do now is to calculate the density matrix of the ground state of the 2-qubit system. And that is just defined. So when I diagonalize, I will get a solution which is a linear combination of these coefficients. So diagonalizing, for instance, the matrix, if I look at the excited states, not the ground state, this is the lowest lying state, I could calculate a row 1, but then I would have different coefficients in front here. Then what I'm going to do, because if I now calculate, so this state, when I diagonalize, I know exactly that that is the ground state of the system. It is the lowest lying state. And this is given precisely by this expression. So if I calculate the entropy of this one, it should not come as a surprise that the entropy is 0. Because even if the state is entangled, it is uniquely defined. So this is what we call a pure state. So a pure state has entropy equal to 0 because I know exactly where I am. However, what I can do now is to calculate the density matrix for the subsystem. If you then go back to what we discussed some 2 to 3 weeks ago, then we could have a ground state, which is a 2-qubit system, which is uniquely defined. We know exactly these coefficients. But when we then project down the subsystem, we cannot tell which state qubit in the system A is in and which state the qubit in system B is. Because these will often be a linear combination of qubit 0 and 1 in system A or system B. So if these states are also uniquely defined, then if I calculate my density matrix for the subsystem, where I now trace out system B, that will simply be the density matrix for the ground state, where I've traced out system B. If I do that, then if this has an entropy which is different from 0, then I will say that these states are entangled and we don't know exactly in which state the qubit is in. So it's a way to get information about a system. And you remember from the Bell states, when we did this exercise, we could show then that the density matrix squared, when we took the trace of that one, was less than 1. So this is just another way of extracting information about the degree of entanglement. So if we now do that, what we would do is simply to take these quantities and calculate the density matrix. So let's now look at the system. So what I'm doing is the following. So I'm going to take this Hamiltonian, the interaction piece, which we have here, this hi, and I'm going to multiply that with a constant. So let me switch over to the whiteboard here a little bit, because I wanted to give you some details. So I just need another 5 minutes and then we are going to stop, but I'm going to repeat some of these things next week as well. So we are going to rewrite the Hamiltonian. So we have this non-interacting piece, And then I'm simply going to multiply with a constant, lambda. So you could think of this lambda as a knob, which you can tune so that you can change the strength of the interaction here. So the computational basis stays the same. There's no change here. So H0 is unchanged, but H1 can be changed. So what we will get then, when we are going to look at the eigenstates as a function, so these are the eigenstates, EI, as a function of this parameter lambda from 0 to 1. So we are going to have a situation here where this state begins here, and then something happens. And then we have another state which goes like this. So this is just a sketch. So this could be the lowest line state, the ground state, E1, E2, and E3. So here, the way I've set it up is a pure 0-0 state. There is no interaction. Here, it's a pure 0-1 state. Here, it's a pure 1-0 state. And here, it's a pure 1-1 state. So the ground state, psi 0, is a linear combination of some alpha 0, 0, 0, plus some alpha 0, 1, 0, 1, plus some coefficients alpha 1, 0, times 1, 0, plus an alpha 1, 1 of 1, 1. And then you can do the same thing for all the other states. So here I can now calculate this rho 0, which is simply the outer product for this state. So when I diagonalize, I'm getting these quantities here, right? This tells you how these states are mixed. So when this interaction strength parameter is put to 0, then clearly here we have to have this state. There is no mixing. So we have a pure state. Pure state, pure state, pure state. Here we have a linear superposition of the states. But what happens here is interesting, because what you're going to see now is that the state here is going to mainly be composed of an alpha 0, 0, 1, plus an alpha 1, 0, or 1, 0. This is going to be the dominating situation. This situation here is often called an avoided level crossing. So what happens is that your state up to a certain point is dominated by this one, but then it changes character. So it means that when you tune this knob experimentally, we do it theoretically, what happens when you move on here is that this state evolves into this state. So I have suddenly an entangled state, which I cannot write out as a pure state. And what we will see then, when I calculate now the entropy of the subsystem, is that we are going, so this state is uniquely defined. So the entropy here is always going to be 1. But when I then project down the subsystem, and I take the density matrix of qubit A and qubit A here, then my system is going to have a mix of qubit 0 and qubit 1 of system A. So that means I cannot tell with certainty in which state the qubit in system A is, and in which state the qubit in system B is in. So let's see how this happens. Let's take a look at it. So I'm going to run a calculation now where I choose a certain number of values. And let's do that. And keep in mind also that we will repeat this next week, because then we are going to look at more details on how also to encode this type of system using the variational quantum eigensolver. So what I'm going to do now is to trace this out and calculate the entropy. So in the code here, so my matrix is a 4x4 matrix, 2 qubits. I'm setting up 40 values. I'm setting these parameters, and you see the diagonal ones. So this is the state 0, 0. 0, 1 as this eigenvalue, 1, 0, and 1, 1. So they're well separated. So if I now diagonalize and run the code, what you will see then is the following. So here, the same as we had on the graph on the whiteboard, this is state 0, 0, state 0, 1, state 1, 0, and 1, 1. Now, one thing which happens here, when I now look at the entropy, so this is the entropy of the subsystem. So the entropy starts increasing, which tells me when it's 0, then I have a pure state, 0, 0 for subsystem A. So that means I know that subsystem A is in the qubit state 0. But then when I increase the strength here, I'm getting linear combinations. And suddenly there's a jump here. And this jump corresponds with the wave function changing character. So let's see that by looking at the coefficients. And so what I'm going to do now is to reduce the number of values to 10. So it's going to be and then I'm going to print the eigenvectors. And I'm going to print them as a function of this strength parameter. So let's just do that. This is a strength parameter. And then I'm going to print eigenvector for the ground state. And you know that the row, so I'm going to print the coefficients of the eigenvector for eigenvector 0, like this. And then I'm going to do the same thing now for the first excited state. So let's see what it looks like. Eigenvector, oh yeah, I just mistyped it here. So let's just do that. I keep mistyping. Sorry for that. I did that one. Here we are. There we are. Okay. Now it should run. So if we now look at, so when lambda is 0, you see 1. This corresponds to us being in a state 0, 0. Now when I increase, you see that the coefficients now change. So here we are in the state, this is the second state. This is in the computational basis state 0, 1. But now you see when I increase it, it starts getting a mixture from the 1, 1 state, whereas the second state has a mixture from 0, 1 and 1, 0. But still, the other one, when you square this, these are just the coefficients non-squared. When you square them, they are basically 0. But now you see that, so my ground state is still dominated by 1, 1. But then at a certain point here, it changes. And this is the point where the wave function changes character. So up to here, it is dominated by 1, 1 and some tiny mixture from 1, 1. But now suddenly, it changes character. And you see now that when you go here at 0.44, the ground state is now a mixture of 0, 1 and 1, 1. So that means that if I measure the qubit in system A, I don't know whether it is in 0 or 1. You see, on the other hand, that the second state now is a 0, 0 state. So if we now look at the figure here, what you will see now, what happens here is that this changes into a linear combination of 0, 1 and 1, 0. This state here becomes a 0, 0. So here it started as 0, 0, and here it started as 0, 1. And now the lowest lying state is a mixture of 0, 1 and 1, 0. So what I'm having now is an entangled state, which when I then project it down to the subsystem, I cannot tell in which state that specific qubit is. And that is what we call a not pure state. And you see that by the entropy that you cannot define whether it's in qubit 0 or qubit 1. And then the entropy increases. But if I look at the entropy of the 2-qubit state, that is uniquely defined. And if you calculate that one, that will always be 0, because you know exactly that you are in that specific 2-qubit state. Now, I'm not running the VQE. I'm actually running a plain diagonalization algorithm. Next week, we are going to run this with a VQE. Now, I just wanted to demonstrate how entropy can be used to tell us whether we have a pure state or not. And this becomes important because it's a measure of entanglement. And when we are going to look later at how to make gates, how we can physically prepare a state which can be used to set up, let's say, a swap gate, then we need to operate on 2 qubits. And the system which we have here, when we have increased this lambda, which you can think of as a knob to experimentally tune the system, when we have come over here, the state is a linear combination of 0, 1 and 1, 0. And the state itself is a pure state, the 2-qubit state, but the 1-qubit state, when we trace the subsystem, is a system where we cannot define whether it's a qubit 0 or 1. And these are ways of preparing states so that we can actually realize gates, as we will see a little bit later. So this simple example of what we call a level crossing, because the 0, 0 state now becomes the first excited state when lambda becomes larger. This is an example of how we can tune interactions in real physical systems and make an entangled state, which we then can use later to make quantum gates and quantum circuits. So we're going to stop here now, because we will pick up this example next week as well. But next week, we will look at the gritty-nitty detail on how to set up the variational quantum eigensolver. So this is just the exact diagonalization which we did now.